Yes.
Yeah.
Professor, you said that we can write our answer for the recitation and just take a picture of it and send it to you. No, I mean upload on the Canvas, right?
Yep. Yep.
And
That's
some of the
that's
questions are
usually
really difficult, and I really don't know how to answer. And
okay.
so
Send me yeah, just try it, and if you're having trouble with it, yeah, we missed office hours today because my stupid computer. But either just send me a note. We can set up uh, office hours outside the usual time, or
okay,
just or send me an email. We can talk about it that way. Either way, like I said before, I don't care if you can't get the answer immediately. Just give it a try, because what that tells me is that I need to teach something better, or I need to take a different approach.
okay,
So don't think you're the only person in that situation. I mean, because today, a lot of things we're going to be doing we haven't really discussed yet. So we'll be getting to it in the lecture today and on Monday. So if you want to take a while to finish this, that's not a problem.
okay. Thank you.
Yeah. No worries there. Any other issues or questions? It's very quiet this morning. Okay. So what I figured we just go through some of these. Like I said, some we haven't really discussed yet. So what I figured I would do is show you the approach to take. And then like certain things like the naming of compounds, we're going to discuss in the lecture in some detail. But I'll sort of give you a brief introduction about how that's going to work. But as far as isotopes and ions and that sort of thing, we can go right to the periodic table and look up that information and get started on that. So I think I mentioned ptable.com is a great place to go because everything's clickable. You can search. You can get information on densities and what kind of compounds and all that sort of good stuff. So shall we start with number one? I mean, it seems to be a good place to start.
Yes.
Okay. All right. So what I'm going to do is let's look at the first two, and then I'll give us an idea of what we want to do. So the very first one, the only information we have is an atomic number of 20 and a mass of 37. And basically, we have to fill in everything else. And the second one, all we know about it is that it has 18 electrons and 20 neutrons. That's pretty much all we know. Now, one thing that we should look at is just look at the instructions. So it says complete the following table for the what? What does it say there? What are we completing the following table for?
Neutral isotopes.
Neutral isotopes. What does that mean? If an atom is neutral, what does that mean? I can hear Googling. I love when I hear Googling in the background. What's a neutral atom?
When the electrons and the protons are equally balanced.
That's right. That's right. So it doesn't have a net charge. there's no net charge. If it has more protons than electrons, it's positively charged. If it has more electrons than protons, it's negatively charged. But because it's neutral, that lets us know that the number of protons and electrons are the same. So for the second one there, we can already fill out something because it has 18 electrons and we know it's neutral. So by definition, it's got to have 18 protons as well. And so we can start there by working out what that particular isotope is. Now remember, what's the difference between an isotope and just sort of like just a regular atom?
Isotopes have the same number of protons but different number of neutrons.
Right. Yeah. I mean, it means it has it's not the average. If we look up on the periodic table and we look up the mass of an atom, it will give us the average mass. That means it's the average mass of all the isotopes, all the naturally occurring isotopes of that atom. Like for instance, carbon has 12 and 13 and 14 as its masses in nature. You're probably aware of like carbon 13 and carbon 14 dating for rocks to figure out how old they are. And so those isotopes are naturally occurring. But for a specific isotope, we'll have an exact mass because we're talking about one that has a precise number of neutrons, not the average number of neutrons that occur in nature. So when we're looking, so we want an isotope name. You can see at the third one here, it says cobalt, then the dash, and then 64. That means that that particular isotope of cobalt has a mass of exactly 64, not less, not more. So we know precisely how many protons and how many neutrons it has. All right, so let's look at the first two. So we've got, the first one has an atomic number of 20 and a mass of 37. So what I will do, let's go to let's go to Google here. So can you see the screen there? We've got ptable.com. Does that show up on your screens?
Yeah.
Yes.
Okay, cool. So we've got an atomic number of 20. So what does that mean, an atomic number of 20? What's the atomic number refer to? The atomic number has a very specific meaning.
Is it the number of protons?
It is indeed. You can say that with some oomph. Yes, it's the number of protons. Because it's the number of protons that defines an element. If two different elements can have exactly the same mass, but different numbers of protons. And even if those two elements have exactly the same mass, they're not the same element. Because the identity of an element is determined only by the number of protons, not neutrons, not electrons, just protons. Because it's the charge of the nucleus that tells you what that element is. So if we're looking for atomic number 20, that's how the periodic table is arranged. It's not arranged in terms of mass, although you will see that the mass generally increases as we go across the table and down the table, the mass gets bigger. But you'll see that the atomic number increases by 1 as we go across, by exactly 1. And the other way to tell the difference between the mass and the atomic mass and the atomic number, the atomic mass is always going to be bigger, and generally the atomic mass is going to be a number plus a decimal and some other numbers. So it's going to be the average. The atomic number is never an average. It's a very precise number. It's going to be a whole integer. So where are we going to find number 20? So we start with 1 and we sort of go across, and we drop down 1 and we go across. Who's number 20?
Ca, calcium.
Calcium, exactly. So right now, so we figured out that it is calcium. And since its atomic mass is 37, we know now that the name is going to be calcium-37. That is the name of the isotope. So that means it is the calcium isotope that has 20 protons, has to have 20 protons, or it wouldn't be calcium. How many neutrons is it going to have?
17.
17, exactly. 17 neutrons. Because the mass of an electron is so small, it's like less than 1,000th that of a proton or a neutron, that the mass of an atom is pretty much completely determined by the mass of the protons and the neutrons. And they're both one, basically. A little more than one, but close to one. And so if it has, so if the mass is 37, that tells us it's got 37 protons and neutrons. All right. So I think that's all the information we need for the first one. So for the second one, we have 18 electrons and 20 neutrons, and it's neutral. So if it's neutral and it has 18 electrons, what's its atomic number?
$18.
18, yeah, it means it has 18 protons. And so if it has 18 protons and 18 neutrons, it's neutral. If it has 18 protons, therefore its atomic number is 18, and therefore it is what?
Argon.
Argon, right. So that is argon, noble gas. And so how many neutrons does it have? It has 20. So it has 18 protons, 20 neutrons. So what's its atomic mass?
38.
38, that's right. So this time we're going to write down for its name, it's going to be argon 38. So let's go back to the table. And see if we can fill this in now. All right, so the first one, let me get my pen. So the first one, we now know that that's calcium, 37. So we can actually write calcium 37. So it's kind of hard to write on the screen at really small. So calcium 37 with a little dash in between. So the isotope symbol is given like this one down here. That's like the official way of writing an isotope. And you can see that it's got the atomic number on the bottom and the atomic mass on the top. So we would write, what's the symbol for calcium again?
Ca.
Ca.
Yep, Ca indeed. So we put a Ca, and we put its atomic number on the bottom. And so we can see from right here, its atomic number is 20. So we put 20 down here. And its mass is 37. So we put 37 there. So that tells us everything we need to know, basically, about what that is. We know it's calcium. We know that it's got 20 protons. We know it has 20 plus 17 neutrons for a total of 37. And we know how many electrons it has because there's nothing here, right there. If there was a charge, that's where we would put it. We'd put a +1 or a +2, or with calcium, it would always be +2 when it's charged. Let's just fill in the rest. So if its atomic number is 20, we know it has 20 protons. And we know it has 20 electrons because it's neutral. And we figured out that it must have 17 neutrons. So that's all the information. So we're finished with number 1. So the second one we figured out was argon 38. Now notice the calcium's actually larger in terms of protons than argon here, but its mass is less. So that's why the periodic table is arranged in terms of protons and not mass, because we'll learn that the periodic table is arranged in such a way that all of the elements that are in one group, which is up and down, all have very similar chemical properties. And we'll learn why that is as well. If we arranged it according to mass, we would have elements stacked on top of each other that really have nothing to do with each other. It's the number of protons that determine its chemical properties, not the mass. So it's more important to arrange in terms of number of protons. So what would be the isotope symbol for argon? What's the chemical symbol, first of all?
AR.
AR. AR. And so we know, since it has 18 electrons and it's neutral, we know it has 18 protons. Since that's its atomic number, we put that here. And then what do we put in terms of its atomic mass?
38.
38.
38, and we put that here. And if it had a charge, which it's not going to, why won't argon have a charge?
Because
It's the neutral isotopes.
Why will argon never have a charge?
It's a noble gas, right?
There you go. It's a noble gas. So it's extremely difficult to get a charge of argon. I don't think it's impossible. I think now some scientists are able to make compounds with argon, but to get it to actually be an ion is extremely difficult. It takes a lot of energy to strip an electron away from argon. So its mass is 38, atomic number 18. And then the rest, cobalt, and for tantalum down here at the bottom, you just do the same thing, okay?
Quick question, if the mass doesn't match the isotope number?
The mass has to match the isotope number, because that's what the isotope number is the mass.
Because the mass for cobalt is 58.9.
Mm-hmm.
Mass given is 64.
Mm-hmm. So that means the average mass of cobalt is 58.9. So that means if you take all the cobalt atoms in the world and measure the average mass of them, they'll come out to be 58.9. That doesn't mean, that means that that's the average. Some are going to be less, some are going to be more. And cobalt 64 is one of those that is heavier than average. Just like calcium here, this particular isotope is lighter than the average mass of calcium. So yeah, this refers to a specific atom rather than the average atom. That's what you have to remember. Any isotope, we're talking about a specific atom, just one, okay? Not calcium, not cobalt in general. So if I want a cobalt in general, I would just put that as CO.
So this cobalt will have the mass of 64.
Yep. So
Okay.
64 there, because that's the mass of that one atom of cobalt. Now, when you're writing a chemical equation, if I was writing a chemical equation, let's say I was writing cobalt plus oxygen gas makes cobalt dioxide, something like that. I don't include the isotopes here, because what I'm basically saying is that I'm just using a sample of cobalt. And so this sample of cobalt, if I just have like a natural sample of cobalt, it's going to have all the isotopes in it. And if I measure the average mass of all the cobalt atoms in that sample, it'll be 58.9. But you can also isolate particular isotopes. Like you've probably, I don't know if you have how much attention you pay to the news, but you remember years ago, maybe this was like before your time, years ago that Iraq was suspected of enriching uranium by using centrifuges. Anyone remember that?
No.
Damn. Sorry, I'm gonna have to come up with a new example. Anyway, yeah, if you want to make an atomic bomb with uranium, you have to isolate specific isotopes that are more radioactive. So you need uranium-235, and you need to separate it from uranium-238. And so 235 is more radioactive, and you can make a bomb out of it. And so you can separate this one. And so once you, and you separate it by turning it into a gas and then spinning it at very, very high speed. But yeah, I'll have to come up with a whole new example, since that was like 20 years ago. Like, okay, never mind. All right, let's see what the next one is. Oops, let me clear that out. So this is just another conversion. Do you want to just do a quick one here? Or is there a particular question that people want to get to?
Could we do number 2? I just wanted to know how you would do it if there's 2 different units involved.
Okay. So this particular one, there's a number of them in number 2. I figured we do like maybe 2 of them. Is this one? This one basically asks you to remember something that maybe you don't remember. So it's a little tricky. Yeah, we'll just do this one, and then you guys can pick the next one you want to do. So this one is oh yeah, it's if someone wants to pay attention to the chat, I can't watch the chat at the same time. So if someone wants to be the official chatmeister, please do so, and just let me know if there's a question in the chat, okay? Right, so this particular question. So what we want to do, right here, we have 2 different measures of volume. So if you remember, liters is basically sort of a standard way we measure volume in the metric system. And anyone remember what microliters are? How big is a microliter relative to a liter? Something's micro. Do you remember if you throw the prefix micro in front of something?
Millionth?
A millionth, right, or 10 to the minus 6. So 1 microliter is equal to 1 times 10 to the minus 6 liters. So you may be asking yourself, what the hell does that have to do with dm cubed? I don't even remember what dm cubed means. Well, that means decimeter. And deci is one of these things we don't really use that often. But when anyone remember what deci means?
10?
10, or actually not 10, but
10th?
10?
10th. So a decimeter is 1 times 10 to the minus, 10 to the minus 1. Let me just erase that. 10 to the minus 1 meters. Or another way of putting it is in how many centimeters would that be? Anyone remember how many centimeters there are in a meter?
-2.
100.
There's 100, right? So if there's 100 centimeters in a meter, how many centimeters would there be in a tenth of that?
10.
10.
10.
Yeah, exactly. So that's the same as 10 centimeters. So if I take 10 centimeters, so a decimeter cubed is the same as this cubed, which is the same as this cubed. And if I cube 10 centimeters, how many cubic centimeters do I get?
1,000.
1,000, that's right. And does anyone remember what volume 1,000 cubic centimeters is?
1 liter.
1 liter, exactly. So that is the, this is actually the definition of a liter. So basically all we're doing here is we're converting microliters to liters, okay? So let's just, so that's 2.33 times 10 to the 5th microliters. And then remember, we want to multiply that by something that turns into liters. So we're going to want to have liters on the top, and we're going to have microliters on the bottom. And remember, whatever you multiply this by has to equal 1, because we're just changing the unit. We're not changing the amount, so we have to multiply it by 1. All we're doing is changing the unit. So whatever we multiply it by has to equal 1. So the top of this has to equal 1. The top and the bottom have to be the same. So whatever we put on the top, we've got to put on the bottom. So what are we going to do here? How are we going to, what sort of relationship do we want to show between liters and microliters? So we can either put 1 liter on the top, or we can put 1 microliter on the bottom. Which
1
would you like?
microliter on the bottom, right?
You can do it either way. That's what
Oh.
I'm saying. You can either do it this way. You can put 1 microliter on the bottom. Then you'd have to put 10 to the minus 6 liters on the top. Or you could put 1 liter on the top and 10 to the minus 6. 10 to the 6th microliters on the bottom. It's the same thing. So in one, you're multiplying by 10 to the minus 6. And on the other one, you're dividing by 10 to the 6th. And it's the same thing. Both of those operations give you exactly the same answer. So it's either way you want to do it. Okay? It doesn't matter. Each of those are equal. 10 to the minus 6 liters equals a microliter. So that's 1. And 1 liter is equal to 10 to the 6 microliters. That's also 1. So either way, you're multiplying by 1. So let's do it this way. So if we're multiplying 2.33 times 10 to the 5th times 10 to the minus 6th, when you're multiplying exponents like that, how do you do that?
You add it?
Mm-hmm. Exactly. This is 10 to the 5th. This is also 10 to the minus 6. You just add them together. So what do you get? You get 2.33 times 10 to the minus 1. And you could leave it like that, or what else, how else could I show that? How else could I express this number without the exponent?
You just move the decimal places to.
Yep, it's there. So then what would I have?
0.233.
Yep. 0.233. You're not done. That's just the number.
Liter.
Liters. There you go. Yep. I'm going to be putting that in all your reports. Units and sig figs for the first couple of weeks, just over and over and over. Just to make that point. Yeah, so that would be your answer. 0.233 liters. Or if you wanted to leave it in scientific notation, that's fine, because the question doesn't say how to express it. So either one would be correct. If I said, you know, in scientific notation, you would leave it this way. And if I said don't express it in scientific notation for some reason, then that one would be right. Okay? All right. So which one? So we can do.
Do we don't find the decimeter from it? Or
Oh, I'm sorry. You're right. That's stupid of me. Yeah, liters and decimeters cubed are the same thing. Sorry. You're absolutely right. So the answer would have been 0.233 decimeters cubed. Man, nice catch. I just got so caught up in explaining what decimeters cubed are that, yeah, I forgot to do that. Yeah, it's just a liter. Oops. All right, so we have 2B, which is just basically using density. C, converting miles to kilometers. And moles of aluminum nitrate. Which one would you like to do?
Can we do 2C?
Sure. Anybody else? That sound fine with people?
Yes.
Can we also do 2E?
Yeah, I'll give you a start on 2E. Okay, show you how to go about it. And you can finish it yourself. But yeah, let's do 2C for a minute. So here, whenever we have one of these questions, I just first like to write down what I'm given. So I'm given 25 miles per hour. And what I want to get to is kilometers per minute. So I need to change two things, right? I need to change miles into kilometers or kilometers, and I need to change hours into minutes. Well, the first things first. Let's change hours into minutes. We can probably do that. So remember, when I multiply this by something, I want to cancel out hours, and I want to leave minutes on the bottom, which means I want to leave minutes on the bottom, and I want to have hours on the top. So I'll be able to cancel hours out. So 1 hour is how many minutes?
60.
60. That's fairly straightforward. And the other one, I want to convert miles into kilometers. And so for this one, I want to have miles on the bottom, and I want to leave kilometers on the top. So now I would just look it up. So let's look it up. Oh, someone's going to look it up for me. Excellent.
1 mile is 1.60934
Okay. 1 mile is 1.60934
kilometers.
kilometers. Okay. So remember, that is 1 because the numerator equals the denominator. And this numerator equals the denominator, so that's 1. This numerator equals the denominator, so that's 1. And let's check and see. Now, this is why I like to keep all of the units there, because this tells me if I've set this up properly. And if I'm doing it on a test, it shows the instructor that I know what I'm doing. I may make a dumbass mistake and, like, my big, fat finger will press, 4 buttons on my calculator simultaneously. So I may screw up the calculation. But if I've set up my calculation properly, I'm going to get most of the points on that question. So miles, I have miles on top. I go across, I got miles on the bottom. That cancels out. I've canceled out my hours already. So those are gone. What do I have left? I have kilometers on the top and I have minutes on the bottom. Yes and yes. So that means I've set my conversions up properly. So now all I have to do is multiply everything that's on the top together and divide it by everything that's on the bottom. Okay, and since this is 25 miles per hour, it's going to assume there's a 1 there. So I just multiply 25 times 1 times 1.60934, and then I divide that by 1 times 60 times 1. Okay, and that should be my final answer. Divided by 60. All right, so I get 0.6705558 kilometers per minute. Is that the correct answer?
No, you have to put it in significant digit, right?
Right, exactly. I would just write sig figs in great big letters and take off half a point because I'm that kind of bad person. So, how many sig figs do I have?
2.
2.
2. Right, there's only 2 here. That 5 is significant even though there isn't a period because it's non-zero. If this were 20, there'd really only be 1 significant digit. And so if it was 20 with a decimal, that would be 2. But since it's 25, it's a non-zero number, both the 2 and the 5. Any non-zero number is significant. So we say there's 2. So how are we going to take this number? How are we going to take that number and reduce it to 2 significant digits?
0.67 kilometers per minute.
There you go. So 0.67. That would be the final. Is that your final answer? Yes, that was my final answer. Yep, good one. And so for this one here, basically all you need to do is convert ounces, find the conversion for ounces to grams, and then give your volume in mils. And mils is already there. So really, you just have to do one conversion there, okay? Just find out how many grams there are in 45.98 ounces of gold. The other thing would be, how many significant digits should be in your answer for that one?
4.
4, right. There's 4 here, and there's 4 here. So your final answer should have 4 sig figs. Okay? All right.
That one, once you convert the mass, then you find the volume, right?
Well, yeah, here, yeah, you find the mass, and so density is mass over volume. So if you know what the mass is,
You just multiply it.
just figure out what the volume is. Yeah. So moles of aluminum nitrate. So we sort of going to be learning, we started to learn a little bit yesterday, that 1 mole, where's my pen? 1 mole is basically the number of molecules that equal the atomic weight of whatever this is. So we need to figure out what the atomic weight of this is. And where are we going to find that out? First of all, we need to figure out what it is, right? So aluminum nitrate. So aluminum, what's aluminum? What's this symbol for aluminum?
AL.
Al. And you're not going to know what nitrate is yet. Or maybe you do. Or you can just look it up. Nitrate is NO3. Now we're not done here because this is an ionic compound, and this is something we're going to be learning about in the next couple of lectures. This is an ionic compound. And how do we know it's an ionic compound? Because it has a metal and a non-metal. Aluminum is a metal, and metals make ionic compounds. Metals lose electrons. So aluminum is going to be positively charged when it's in a compound with a non-metal, and it loses 3. Aluminum always loses 3 electrons. So the charge on aluminum is going to be +3. Nitrate, anyone want to look up what the charge on nitrate is? You can just look that up.
Is it negative?
Yep, has to be negative. Since aluminum is positive, nitrate has to be negative because any compound has to be neutral.
-1, right?
Yeah, nitrate's -1. So the charge on nitrate is -1. Nitrate is also what we call a polyatomic ion. So this whole thing, nitrogen plus 3 oxygens, this whole thing together, and it acts as a single group, has a charge of -1. So how many of these am I going to need to balance out the charge on aluminum?
You don't. It's already balanced. Right?
It isn't. This is not the formula for aluminum nitrate. This just says this is the formula for aluminum. That's the symbol for aluminum. That's the symbol for nitrate. It is not balanced.
Oh, you put a 3 at the end.
Where do I put the 3?
The parentheses on the right.
There you go. Yeah, I need 3 of these because if it's a compound, it has to be neutrally charged, because if it isn't, it's an ion. So a neutral atom can't have a charge. A compound can't have a charge. Only an ion can have a charge. Now this is a compound, but it's an ion, so it has a charge. So we call it an ion. We don't call it a compound because that infers that it has no charge. It's an ion. So aluminum is always +3. Nitrate is always -1. So we put these together. So 3 times -1 is -3. So I have +3 and a -3 together. So my charge is 0 now. So this is the formula for, let me just erase that. This is the formula for aluminum nitrate. AlNO3 brackets 3. So if I want to figure out the atomic mass of this, I could just look it up. It would be one way. Well, the other way, let's figure out how many atoms we need, and we'll do it old school. So how many atoms of aluminum am I going to have? So in one mole of aluminum, or in one molecule of aluminum nitrate, how many atoms of aluminum are there?
Is it 1?
Yeah, 1. This is my formula. Whoops. This is my formula right here. So I would have 1 aluminum. How many, 1. How many nitrogens would I have?
3.
3.
3, that's right. I have 3 nitrogens. And how many oxygens would I have?
6. 9.
9, that's right. 9 oxygens, because I multiply everything inside here by 3. So I have 1 aluminum, 3 nitrogens, and 9 oxygens. So let's go back to our periodic table, our dynamic periodic table. And let's find aluminum. Where is aluminum? Al.
13.
13. But that's not the mass of it, is it? What's the mass of aluminum?
26.981.
Yep, 26.982. Uh-huh. What about nitrogen? What's the mass of nitrogen?
14.007, but you multiply it by 3.
Do we divide it by 3?
You multiply it, right?
Multiply it by 3 because there's 3 of them, right? So multiply that by 3. And then oxygen, what's the mass of oxygen?
15.999.
Yep, 15.999.
Multiply.
999. So let's go back. Oh dear, all of my beautiful work. Right, so we wanted to have, so 1 aluminum, that's 26.982, and 3 nitrogens, so that's 3 times 14.007, and 9 oxygens, and that's 9 times 15.999. All right, someone want to do that math for me, please?
212.994.
What's the total?
212.994.
Okay, excellent. Now, what does that number mean? That means that's the formula mass or the compound mass of aluminum nitrate. What does that number mean in terms of moles? Because on the periodic table, the masses are given in like atomic mass units. But what the hell does that mean, like in terms of moles? 212.994 atomic mass units. That doesn't help me.
You have to convert it, right? The Avogadro.
Yeah, someone mentioned Avogadro's number. Now, I personally think that Avogadro's number is the most overrated number in the history of science. It just confuses people. I generally don't use it or don't teach it. Although I think stupidly there's a question involving Avogadro's number in this stupid thing. Anyway, atomic mass units, don't even worry about Avogadro's number because it doesn't help us here. What atomic mass unit actually means, what does that mean in terms of its mass per mole? If I have 212.994 atomic mass units, what's its mass per mole? Don't even worry about it. Avogadro's number is not going to help you. Let me put it this way. If the mass of aluminum is 26.982, what's the mass of 1 mole of aluminum?
26.92
Or 26.982 what?
grams.
Grams. Yeah. So atomic mass units, all that means is that's how many grams there are of it in a mole. And so that's the important thing to take away. Not Avogadro's number, because that just basically, that only tells us the mass of 1 atom. And we generally don't really care about the mass of 1 atom, because in a lab, how many times are you going to measure the mass of 1 atom of something? Never. That's when. So when you actually measure something, you measure something in grams. You don't measure something in atomic mass units, because there's no way to do that. Grams you can measure though. And so what to remember is that atomic mass unit, all that means is 1 gram in 1 mole. That's all that means. And so my mass of aluminum nitrate is 212. Where's my eraser? All that means is that is 212 grams per mole. So I take my 250 grams, I multiply that by something, and I get moles out. So what am I going to do here? How am I going to get from grams to moles? I can't do this because I've got grams on the top.
I'm gonna switch
Right.
it. Moles on top and grams on the bottom.
There you go, exactly. So I just put moles on top and 212.994 grams on the bottom. That way grams cancel and I'm left with moles. So that's how you would do that. So what I really want you to take away, what we're really going to learn about what moles are. Mole is just the way of calculating the amount of substance that reacts with something else. Because we generally measure everything in grams, right? But molecules don't react in grams. They don't. Why don't they? Well, because they're all different masses. What atoms and elements and compounds do is react to each other in terms of moles. That's how they react. So 1 mole of aluminum plus 3 moles of nitrogen plus 9 moles of oxygen give you 1 mole of aluminum nitrate. That's how it works. It's not 1 gram of aluminum and 3 grams of nitrogen and 9 grams of oxygen. It doesn't work that way. Everything's in terms of moles. So that, a mole is just the measure of the amount of reactive stuff in a mass. That's all it is. And so don't worry about Avogadro's number because it really doesn't tell you anything about the relationship between grams and moles. That's just the number of atoms in a mole, and we generally do not care about the number of atoms because we're not calculating them, okay? And I apologize, I think there is a question about atoms in here. I promise I will never put a question about atoms on a test because I don't care about Avogadro's number, and neither should you. There is a law coming later on that Avogadro also came up with that is a lot more important than that. But not saying that Avogadro was a bad guy. He did a lot of cool stuff. All right. Now let's clear this. So here this is something we're gonna learn coming up. So I'm not going to spend a whole lot of time on it. I'll do a couple of these sort of just to give you a hint as to where we're going. So we're going to be learning how to name things. And it's important because, you know, if I tell you to, like, you know, get me some aluminum hydroxide and do a reaction with it, you're going to need to know what the hell aluminum hydroxide is, right? So let's do aluminum hydroxide right there. So as I mentioned, we haven't talked about the 2 different kinds of compounds, but let's talk about them now. Generally 2 different kinds of compounds. There's covalent compounds and there's ionic compounds. And the difference is, an ionic compound has charges in it. So it usually has a metal, which has a positive charge, and a non-metal, which has a negative charge. And let me go back to the periodic table, because this is something we're going to be learning. There's sort of 2 general areas of the periodic table: metals and nonmetals. And surprisingly, almost all of the periodic table are metals. Like everything, group 1 all the way to group 12 are all metals. And even, I don't know if I can write in here. Let's see if I can write in here. Oh, I can. Excellent. So these are nonmetals. Just those few elements. That's it. Everything over here, and all of these, and all of these are metals. So like I said, the vast majority of the elements in the periodic table are metals. And metals like to lose electrons, so they become positively charged. The nonmetals generally become negatively charged, with the exception of the periodic, of the noble gases, which don't. They're non-reactive for the most part. And so really, you only have these few compounds here. Carbon, nitrogen, oxygen, fluorine, all of these, and that's it. They become negatively charged. Okay, and that would be an ionic compound. Now, if I have two nonmetals reacting with each other, like carbon and oxygen, or carbon and nitrogen, or phosphorus and oxygen, those sort of things, they form covalent compounds, which aren't charged, meaning they share electrons equally. Not quite equally, but they share electrons. Whereas ionic compounds are charged. One element gives its electrons away, and the other element takes them and keeps them, so that they have a charge on them. So let's go back. How do I know when something is a covalent compound and something isn't? A covalent compound is two nonmetals. An ionic compound is a metal and a nonmetal. So let's just look at some of these. Sodium sulfide, would that be ionic or covalent?
It's covalent.
Look at your periodic table, if you have your periodic table in front of you. What's sodium? Is sodium a metal or not?
Metal.
Metal.
Sodium's a metal. So what kind of compound is that?
Covalent.
Ionic.
Ionic. If it has a metal in it, it's ionic. Because metals love to give away their electrons. They can't wait to give away electrons. In fact, sodium wants to give away its electrons so bad that if you throw, anyone seen a video of someone throwing a piece of sodium into water? What happens? Roger, you know what happens when you throw sodium into water. What happens?
It kind of explodes. It catches on fire and then explodes.
Yeah, it explodes. So it really wants to give away that electron. Sodium can't wait to give away that electron and become sodium plus. And we'll learn why that is when we talk about the electron configurations of sodium. But for now, we know that sodium is a metal. Metals like to give away electrons, and therefore it's going to be positive. Now, sulfide, what do you think that means? Sulfide. Sounds like a certain element.
Sulfur.
It sounds like sulfur, right? And because it is. And so what the "ide" means is that it has a charge on it. It's no longer sulfur. Sulfur is this, right? That's just sulfur by itself. Sulfide means it is charged. And when sulfur is charged, it has a charge of -2. It's just below oxygen. Oxygen, and we'll learn this in class as we go through. Oxygen is a charge of -2, and so does sulfur. So this makes an ionic compound. The metal has a charge of 1, +1, and the nonmetal has a charge of -2. How are we going to put those things together so that they have no charge?
So the sodium you have to multiply by 2.
So I would have this, NaS2. Is that what I'd have?
No, just the Na.
Oh, I put a 2 on the sodium.
Yeah.
That's right. Take that away. Yeah, I put a 2 there. So that way I'd have 2 positive charges and I have 2 negative charges. And it's balanced. So that would be sodium sulfide. Okay? Let's look at the next one. Now this has a Roman numeral in it. And we'll learn that a Roman numeral means automatically it's an ionic compound. And we should pretty much know that anyway because it's nickel. And even if we don't know anything about nickel, we know that nickel is a metal, right? I mean, there's nickels, they're metal. It's probably metal. But what does the 2 in brackets mean? Let's go back to our handy dandy periodic table. So notice we've got these, let me draw. So we said these are metals, and these are metals in here. But there's something different about these in the middle. What do we, anyone know what we call those in the middle?
Metals.
Yeah, I think I heard you.
Transition metals.
Yeah, they're transition metals. You know what that means? It's okay if you don't. Just take a guess. Does anyone know what it means?
Do they have properties of both metals and nonmetals?
No, that is the metalloid. That's a good guess, but no, those are the metalloids. And those are these here. Those are these elements. Boron, silicon, arsenic, antimony. Those are metalloids. And we'll learn that metals are conductive, nonmetals are non-conductive, and metalloids are semiconductive. Like you'd find in a semiconductor. Interesting. Yeah, so that's why silicon is a semiconductor, and we'll learn a little bit more about that later as well. Since we're in Silicon Valley, we might as well learn about it, right? So, no, those are the metalloids. So transition metals do have, there's something different about them and these metals here. I'll give you a hint. These metals in the first group, when they get charged, always have a charge of +1. Those are the alkali metals, and they always are +1. Second group, we call those the alkali earth metals, and they always have a charge of +2 when they become ions. Now these metals in the middle, all these metals in the middle, not quite all of them, but the vast majority of the transition metals aren't always +1 or +2. What do you think they can do?
They have like 3 or more.
Some of them. What they mean, but basically what the transition means is that they have different charges depending on what atom or ion it is they're bound with. So for instance, nickel we have right here. The reason why it has a 2 with a brackets around it means in that particular compound, it has a charge of +2. Other compounds, it has a charge of +1. It depends on what it's bound to. If it's bound to something that's pulling its electrons very, very tightly, it gives up 2 of them. If it's bound to something that isn't pulling on its electrons quite so much, it only gives up 1. And there are certain elements like, where are we? Where's chromium? Chromium. Chromium can have a whole lot of different charges. It's anywhere from like +1 to +6. And so, that's why I like ptable.com, because I click on properties or compounds, chromium, and it shows all the different things it can make. So it can have a charge of 1 or 2 or 3 or 4 or 6. It can be a lot of different charges. And so a transition metal means that it's not always the same charge. And so if we're going to write the formula for a compound, a transition compound like nickel, we have to say what charge it has, or else we don't know what the formula is going to be. And we only write this, we only put that there if it's a transition metal and it tells us what its charge is. So automatically we know that that is nickel +2. And it's important we know that, because if it's nickel +1, it's going to have a different formula. And so we would put nickel brackets 1. And remember, we only use the brackets with the Roman numeral if it's a transition metal. Some of those metals that are in the transition area always have the same charge and we don't use it. Like for instance, aluminum is in there, but it's always +3. And silver is in there, but silver is always +1. So there's zinc is in there. It's always +2. I'll show you the exceptions, but the vast majority of them have different charges. Nickel's one of them, and so we use the Roman numeral to tell us what charge it is. Now the other one is phosphate. So phosphate is the non-metal ionic part, and phosphate is another polyatomic ion that has this formula. Now, anyone tell me what the charge on phosphate is? You can look it up because you're not going to know.
-3.
-3. So that means the whole thing has a charge of -3. So nickel has a charge of +2, phosphate has a charge of -3. What's the formula of nickel 2 phosphate going to be? In order for those both to balance, for all the charges to balance out.
Ni3PO4 2.
Excellent. Yeah, we can do the crisscross applesauce method. We just put the 3 here and the 2 there. That's a fairly straightforward thing to do. Basically, we just want, both charges to equal each other. So sometimes we just multiply them. Make this 6, make this 6. How did we get there? This by 3, that by 2. So yeah, so our final would be Ni3PO4 2. There you go. Now, let's look at this one, elemental fluorine. Now what that means, fluorine is a metal or non-metal? Where's fluorine in the periodic table?
It's a
It's F.
It's a non-metal.
It's a non-metal. In fact, it's pretty much the most non-metal element there is. And we'll get into why that is in a minute. Yeah, it's super not a metal. So if we find fluorine by itself, so this is not going to be ionic. So we find fluorine by itself. It is not going to exist as just F. And we'll learn why that is. Basically, it's because everybody wants to have 8 electrons to share or play with. Fluorine has 7, and we're going to write them like this. And again, we're going to learn this in class, so don't freak out if you don't know this already. So it is 7 electrons. Where am I? Oh, wait a minute. See if that works. No. Damn it. I'm gonna have to draw them. Okay. 1, 2, 3, 4, 5, 6, 7. And the other fluorine is going to look the same way. 1, 2, 3, 4, 5, 6, 7. So what's going to happen is that those 2 fluorines are going to share this one so that they each have 8. And they're going to look like this. F with their 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And this shared pair will make 8 for both of them, meaning that fluorine doesn't exist as just F. It exists as F2. And we're going to learn this stuff when we get into bonding, okay? So right now, don't worry that if you don't know a lot of these yet, because we haven't got to them. I sort of just wanted to introduce them, okay? And periodate, man, I need more coffee. Periodate ion, yeah, we can look that up for right now, because Like I said, we're gonna talk about that in class.
Is it the same thing as hydrotic acid? Or is that hydrotic acid is...
That's a good question. Here, I'll show you. So periodate ion is IO4 minus. So periodic acid is just HIO4, and it's not charged. And we'll learn about acids and bases a little bit later as well. All right, so let's get to the next one. Oh, so names. So names, we'll just do like I said, we're gonna do this in class. We'll do some quick names, and I'll introduce you to how we name things. So let's just have a quick look and see if we can identify ionic compounds and covalent compounds, okay? So the first one, we have K and we have Br. So remember, oh, not remember, you haven't been taught yet. Usually if we put the metal first and the non-metal last. So what we would ask is K a metal?
Yes.
Yes, it is. It's way to the left. Everything to the left of the periodic table is a metal, and everything to the right is a non-metal, and K is way to the left. So it's very, very much metallic. And what is it?
Potassium.
Potassium. We just write down potassium. That part's easy. And Br, is that
Bromide.
metal or non-metal? It's got to be a non-metal, right? So we have a metal and we have a non-metal. So it's an ionic compound. So this is ionic. And we'll learn why it's important to have when you're naming something, whether it's ionic or covalent. So it's ionic, it's potassium, it's Br, and someone told me what Br was. It's
Bromide.
Br is not, it's bromine, but it is bromide in the name because, yeah, it's because it's ionic. Bromide means it has a negative charge. So Br minus is bromide, and Br by itself is bromine. Okay, so we would say bromide. So this is potassium bromide. All right, let's do the next one. Na3.
Yeah.
So is that a,
Okay.
is that an
Solo ya lo escuchaste. ¿Has hecho solo dijiste o ya lo escuchaste?
She can come out and play in a minute. All right, so Na, is that a metal or a non-metal?
It's a metal.
It's a metal. Which metal is it?
Sodium alkali.
Sodium. It's an alkali metal. It's way metallic. So we just write down sodium. And what is P?
Phosphite.
Phosphate. P is phosphorus. P is phosphorus. But it is a non-metal and it's negatively charged. So how would we change phosphorus to ide? That phosphorus,
It has a negative charge.
it has, so phosphorus means P, neutral. But when P is charged, it has a -3 charge. And what do we call it?
Phosphide.
Phosphide, there you go. Phosphide, so that would be sodium phosphide. Now, the third one is tricky because third and fourth one. I'll do these first two, then The other ones we can come back to after lecture. But this makes a very important point. Is that an ionic compound or a covalent compound?
Covalent.
That's covalent, right? Because both nitrogen and oxygen are nonmetals. That means they share electrons. They don't form ions in this. So nobody has a charge. They're sharing electrons. Now that's something very important because since they're sharing electrons, nonmetals can share electrons in all kinds of different ways. They can form single bonds, like chlorine to chlorine, that forms one bond. Now a bond is one shared pair of electrons. However, oxygen with oxygen forms two. Those are two pairs of shared electrons for a total of 4 electrons being shared. And when nitrogen forms a bond with itself, it forms 3. That's 6 shared electrons between them. And so if I have two nonmetals, they can share electrons in all kinds of ways and just by looking at them, I don't know. Because for instance, when nitrogen is bound to oxygen, it can make 1 or 2 bonds sometimes. It depends. So I can't just say nitrogen oxide. That's not enough information. Just like we learned yesterday, we were talking about carbon and oxygen forming compounds. Does it form just one?
No.
No. It forms carbon monoxide, which is CO, and it forms carbon dioxide, which is CO2. So if I just said carbon oxide, you don't know what compound I'm talking about. And the same thing is true here. Nitrogen and oxygen can form all kinds of compounds, like literally dozens of different compounds. And so just saying nitrogen oxide is insufficient information. So if I have a covalent compound, you have to say how many atoms of each one are in the compound, or else there's no way of knowing. Okay, so here I would have to tell the person, if I'm describing this nitrogen oxide to someone, I have to say how many of each one are there. So I would have to say di-nitrogen oxide. Or I could even say dinitrogen monoxide, but generally if you don't, you can sometimes leave the monoxide off, but dinitrogen monoxide would be the name. Monoxide. So that tells me there's 2 nitrogens and 1 oxygen. Okay? And you only have to do that for covalent compounds. The reason you don't have to do that for ionic compounds, let me show you. So let's go back to this one. Let's go back to sodium phosphide. The reason we don't have to say trisodium monophosphide, phosphide, that's not the name of it, because sodium always has a charge of +1. Always. That's the only charge it ever has. Phosphide only has a charge of -3. That's the only charge it ever has. So there's only one way for those 2 elements to combine, 3 to 1. And if that's the only way they can combine, I don't need the tri and I don't need the mono. I just say sodium phosphide. And that's the case here. Here, I've got manganese and I've got oxygen. So the name here, oxygen, has a charge of -2. So the total charge of the oxygen is -4. And so I would write down, so manganese has a charge of what? Manganese oxide. So if my oxide part has a total charge of -4, what must my charge on manganese be? I've got one atom of manganese, and it needs to balance out a charge of -4. What must its charge be?
4
4
plus.
plus, exactly. It's got to be 4 plus. So I would just write 4. Manganese 4 oxide. Because manganese can have either 2 or 4. And so I just write down manganese 4 oxide. And because it's ionic, I'm telling you this charge is +4, and oxygen is always -2. So there's got to be a total charge of -4. So there has to be 2 oxygens. So this has to be MnO2. And we'll learn, so we'll learn more about this. I sort of just want to introduce the fact that when it's a covalent compound, those atoms can go together in a lot of different ways. So you have to lay out how the number of atoms in it, because it can be a lot of different things. But when it's an ionic compound, there's only one way for those things to come together. If you tell me what the charges are, there's only one way for them to come together. You don't have to spell out how many atoms there are. I can figure that out on my own. Okay? So we've sort of basically done these already. Let's just do one. We've sort of done this with question number 1. Let's just do one of these. Any particular one you want to do? A, B, C, D. I mean, the rest I left off because like 6 is basically the same question. I should have just cut question 6. C, so did I hear C? Or B? Doesn't really matter. They're all basically the same question.
C.
Is there anyone in particular?
B.
B, sure. Why not? B. Right. So we're going to write the symbol. So you remember how the symbol goes. We write the symbol. Whoops. Whatever it is, and we put the atomic number here. We put the mass up here, and we put the charge over here. Okay. So if we go to the periodic table, what has 53 protons?
Iodine.
Is it iodine? Iodine? Iodine. Okay. So I, right? And so 53 goes down here. Now, if it has 53 protons and 74 neutrons, what's its atomic mass?
$127.
127. So we put the 127 up here. Now, if it has 53 protons and 54 electrons, what's its net charge?
1.
1 plus or minus?
Plus.
Electrons are negatively charged or positively charged?
Ion.
Charged, so -1.
-1, right. So electrons are negatively charged, protons are positive, P for positively charged. And so we have one more negative charge than positive, so we just put minus. You can't put -1 if you want, or just minus is fine. Either way. So this would be the symbol for that particular ion. So that gives us all the information about it we need. We know what element it is, we know what its mass is, and we know what its charge is. That's pretty much all the information you would need for that particular ion. All right? And the rest of them are pretty much the same as that. So just quickly, let's go to the last question. Oh, yes, question? Is there a question there?
No.
Okay. So what I was going to do is just go to the last and show you how to do the last one. Like I said, we're going to go over a lot of these in class, but this is one. This basically tells you the difference between ionic mass and the average atomic mass. An isotopic mass and the average atomic mass. Man, I'm losing my ability to speak. So, a certain element has these atomic masses with these particular abundances. So what we need to do is figure out what would the average, if we took all these together, and this is how you calculate average atomic masses. So the way we do that is we just take the abundances. So it's 90.92%, 19.99. It's 0.26%, 20.99, and it's 8.82%, 21.99. Now, what's the difference between each of these? This one weighs one more. This one is the mass one more. What's the difference in these three isotopes? Between isotope 1, 2, and 3. What gives it the extra mass?
Neutron and extra neutron.
Right, there's an extra neutron, exactly. So 1 has the fewest number of neutrons, 2 has 1 more, and 3 has 2 more. So what's the average going to be? Basically, all we do is convert this percentage into an actual number. So how do we convert percent into a number?
Multiply by that percentage over 100.
Yeah, just divide it by 100, right? Just divide this by 100, divide this by 100, divide this by 100. So multiply this by 0.9092. And what do we multiply the second one by?
.0026.
0.0026. Yeah, let's see. 1, 2. Yep. And the third one, what do we multiply that by?
.0882.
0.0882. Yes. So this just tells us 90% of the total is going to weigh this much. This much of the total weighs 21. This much of the total weighs 22. And so we're just going to basically add the mass of each one, how much it brings to the table, how much it contributes to the average. This will contribute 90% of it. This one contributes less than 1%, and this contributes almost 9%. So we're just multiplying the mass by its contribution to the average, okay? So so number 1, what number does that give us? 99.99 times 0.9092.
$18.174908.
18.174.
4908. 8.
9. Okay, that's probably enough significant digits. We'll worry about the significant digits a little bit later. So 2, what does that give us?
0.05457.
7. Okay, and the third one?
1.939518.
93952. Okay. So let's add them all together. What do we get?
$20.169.
169. Okay, so question is, how many significant, quiet,
3.
how many, now this goes back to how many significant digits. Remember, when we did significant digits, there was a difference in multiplying and adding and subtracting. So the first thing we did was multiply. And here, this number here, let me just, this number only has 2 significant digits, right? This 0.26 only has 2 significant digits, but here they are. Notice how far they are behind the decimal place. These two numbers, 90.92, 19.99, both have 4. So here's our 4 significant digits for that. And 8.82 has 3 significant digits. So here would be our 3. So how many significant digits should there be in our final answer?
Are we adding the total of the significant digits?
Nope. Remember, when we add significant digits, it all goes to how many significant digits there are past the decimal place. And so we're limited by how many significant digits there are past to the right of the decimal place. And here, this one is limited to 2 past the decimal place, and this number also 2 past the decimal place. So how many numbers past the decimal can our final answer have?
2.
2, right. So we can have as many of the left side of the decimal place as we want, but we're limited to 2 on the right side of the decimal place. So what should our final answer be?
20.17.
Yes, exactly. 20.17 is our final answer. So that's why this is a really good question, because it makes you think about both significant digits, adding and subtracting, multiplying and dividing, as well as what does abundance mean, and how are we going to calculate, how are we going to use information about abundance to calculate an average. So this is our final answer. So AMU. So a number and a unit. Okay, any other questions? I know there's a lot. There's a lot of this you won't be able to do yet, but come back to it after the lecture tonight and on Monday. And you can also, you use your textbook, and you can look these things up on the tubes. There's lots of, I put a bunch of really good videos on the YouTube site from both Professor Dave, who I find to be a lot of fun and informational, and Crash Course. There's a number of really good ones in there.
I have a question. Will you be providing like a reference sheet as far as like
Yes.
doing it?
I said I was going to do that yesterday. I forgot, but yeah, there is a general reference sheet. I'll just post it on Canvas of the sort of things you'd be expected to have at your fingertips when you're taking a test. So yeah, it has all this sort of information, like, the isotopic mass. Obviously, you're not going to be expected to know what all the atomic masses of the elements are. I mean, hell, that's just ridiculous. But I mean, so you can have a periodic table with you. And all of these things that you need to convert, like, ounces to grams and all that kind of stuff, would have all that in there too. But right now you can just look them up. So
Are we able to also have a calculator as well?
of course, my God, you can't, you think I would expect you to do this last question without a calculator? It's impossible. It's impossible to do without a calculator. Yes, I'll post the reference sheet. I'm actually writing it down so I don't forget it. I'll forget it anyway, but at least I'm writing it down. Cool. Yeah, so remember, if you're stuck on any of these, and don't worry about them for a while. I mean, this isn't due till a week from today, and you can still, have another week to do it. That's fine. I'm not much of a stickler for a week or two late. 3 or 4 weeks, I get a little prickly. But if you're just totally stuck, yeah, just email me, and either we can work it out over email, or we can set up a meeting, or you can come to office hours if I ever remember to have them and my computer doesn't explode. Next week, Tuesdays and Thursdays, or during the next recitation section, you can ask questions about pretty much anything. So is that anything else before we go? Oh, okay. Go ahead.
And number 5C, because I tried to answer it, is it 31 with the mass, and then 15, the atomic number, and then the symbol, and then do I just put like 3 with a negative charge on the side?
Number 5C?
Yeah.
Okay. Where's my pen? Here we go. 5C. So what element is that? 15.
Phosphorus.
Right? Yeah, phosphorus. We put phosphorus. There's the number. There's the mass. And then where do you put the charge?
I put the charge right beside the symbol. 3,
Yep.
-3.
Right there. Done. Yep. That's it.
Oh, okay. So that's the answer already.
Mm-hmm. Yeah, so phosphorus always has a charge of -3. And so if it's in an ionic compound, it's always going to be -3. So you don't have to say, diphosphide or triphosphide. We're going to know, depending on what metal it's with. So if it's with sodium with a charge of +1, it's going to be this. If it's with calcium, which always has a charge of +2, it's going to be this. Because the charges always have to balance. So you don't have to, as long as we know what the charges are, we don't have to spell out how many atoms. We're expected to sort of figure that out for ourselves. Okay?
Okay, thank you.
All right. I will see you guys in a little while, in 4:15, okay?
Thank you.
Yeah.
Okay, thank you.
Okay, thank you. Thanks for coming. Thanks for so many good questions.